Are we set? Okay, so we're ready to go on to the next talk, which certainly has the most interesting title of the whole conference. So you'll have to wait a moment. I'm not going to give the remainder of the title just to keep the mystery going. So this is a remote presentation. Paulo Ney de Souza, and his talk is entitled "A Family of Strippers."
Thanks everybody for being here. I'd like to talk today about a program that's been quite a while in the making. I first met this problem at the mid-80s when I tried to write unsuccessfully something to separate mathematics from text, and basically to extract text from a LaTeX file and figure out for the first time how hard it would be. Soon after that, a program appeared called DTEC, based on LaTeX, and for quite a while it was an extremely useful program. But LaTeX evolved rather rapidly from a simple $sign and to separate mathematics from text. We evolved into a number of environments, and the problem became more difficult, and today DTEC is not able to act on the simplest files that you can feed it. I tried then to sort of use the same approach, which was to list the same approach used by DTEC, which was to list all the environments and how to treat each one of them. You know, if you want to extract the mathematics inside it, if you want to extract the text inside the mathematics that is inside an environment, and deal with each one of the cases, probably using some more modern tools for doing the parsing. There's a lot of modern tools today to do parsing of programs, stuff which is way better than what we had back then, which was LaTeX and the tools that accompanied. But even then, you know, we don't have a full TAG parser independently of TAG itself. And this talk is about, you know, the challenges of using a pseudo-parser, you know, something that parses part of the text of a LaTeX file, and using it in order to extract mathematics and extract text so that it can be analyzed separately as one may need it. The uses for it are obvious. You know, my first use was spell and grammar checking, you know, but today machine translation of technical books and full text search, you know, training of large language models, accessibility, it comes as one of the requirements that one really needs to know the boundary of mathematics and text within a PDF file, within a source file for that matter. LaTeX is a programming language, not a markup language. So if you look from that view, any tool that reads a TAG file without running TAG is basically writing its own interpreter. And that interpreter is bound to be incomplete unless you put a lot of time into it. what makes it so hard? It's, the language is, first of all, we have a problem which a language which is Turing complete, contains a Turing complete macro system, and user-defined commands everywhere these days. The files are extremely more complex today than they used to be, and optional arguments, stare variants, cat codes, meet document, verbatim environments, math notation versus math prose, and on top of it all, we have the multiple language per document problem. In science, for example, it's extremely common, not just in citations during the text, but on bibliographies that extend over several different languages, including right-to-left scripts, CJK, language that have ligatures which are specific to the language, and even fonts that have discretionary ligatures which are specific to the particular font. So that complexifies the problem even further. So my idea was to I told you that there are some very developed tools for doing parsing these days, but I shy away from dealing with them and try to use ready projects which have been tested and established in terms of parsing tech, and I choose the four that I consider to be the top ones, which is LaTeXML, LaTeXTom, TechSoup, and Pandoc, and then use them as a module inside a program, almost in a way that you could replace one with the other, using them just to parse and to provide the tree with the separation between text and mathematics, and also to experiment to see which ones would provide the best results. LaTeXML was the first one. It's an ambitious approach. We re-implement stack expansion engine in Perl, and it produces XML, MathML, HTML, handles almost everything that you would have on a normal file, on a standard file in LaTeX. It deals with a large percentage of the files which are contained in the archive, for example. And it's also in active development, supported by NIST and AMS and a few others. For text extraction is very accurate for well-behaved documents, and allows the mathematics to become MathML. The limits are that it's slow. It has a very complex. It's not part of TechLive. It fails on certain macros, and it has no multilingual text separation. On text separation, you do want each language to be separated in an independent file, and if possible, for those files to be tagged with BCP47 so that you can easily feed into other tools like language tool or spellers for the particular languages and proceed with analysis. None of that is possible with LaTeXML. LaTeXTom is as a parser which is directed to certain specific and limited commands. So if you want to, for example, obtain metadata out of a file, the author, the title, the pagination, the address of the authors, and so forth. It's an exceedingly good program, but in order to parse a general LaTeX file all the way down to the end and do extraction at every change in between mathematics and text, it lacks and is an incomplete parser by design. It's not built to parse the whole document. It's built to parse only certain specific parts of the document that you may need ahead of time. It's fragile on complex macros, absolutely no language awareness, and is minimally maintained these days. So you even end up with commands which are unrecognized inside text nodes, which is undesirable. Then the next one that I tackled was TechSoup. It's one of the first times that Python met LaTeX very successfully, and this is built on sort of the same ideas of beautiful soup, and I guess even the same framework, and it parses text into a navigable tree, which is really, really nice, and allows you to sort of pick up each one of the elements and analyze it for mathematics and for text and separate them. It handles balanced braces, optional arguments, and is good for scraping content, and that's mostly used for scraping contents. The limits of TechSoup are that there is no macro expansion, breaks on very simple stuff like verbatim and listings, absolutely no language separation, and fails on very simple unbalanced braces, and most of the use of it is as I said, for text extraction, for scraping content out of LaTeX files. And then the next one that I approached was Pandoc, and Pandoc has a different approach. It is most of you know already what Pandoc is, but Pandoc is a Swiss knife tool that allows you to change formats among a humongous amount of formats, and it reads the LaTeX tree, and you're able to even extract plain text out of it right away. But most beautifully, you can insert some markers on it with a pre-filter, and then establish what you want it to do with certain environments that it doesn't know about, and then and later with the processor itself, extract what you want out in text and what you want out in mathematics, and deal with them appropriately. If you compare them, you can get an idea right away. LaTeXML is the second most capable one, and Pandoc is very able to deal with it, because it doesn't require any. None of those require any tech run. They run by themselves within their own environment, and Pandoc is extremely fast and is able to do the separation very well. None of them handles multilingual ligatures, for example, and the way that we chose to build this is almost in a way that you can use this as a plug-in to the main program. So you can basically choose to use LaTeXML, LaTeX Tom, TechSoup, or Pandoc, and run to get your extraction. So how does this work? It works very much in the same way that the old DTAC worked. Some rejects, some heuristics, and inserting markups in the text when you want things to be sorted out in a different way, and then picking them up later. Listing the environments that you need specific treatment. Some environments are scraped altogether. Some environments are searched for text within math mode, and some environments are, discard the environment and use the full content of the environment in a way that you can update this list as you go, so that if you write your own environments, for example, you can add this to a list that will be searched and that will be used for the extraction. The Pro stripper, the first one is literally, the core idea is to use regex, parse it up and try to tell them which environments you want and which environments you don't. The Python strip is a step forward from that, but it almost works exactly in the same way. A dictionary must be maintained with the list of the environments, and how you want it, it to be dealt with. But it contains no font ligature awareness. Math handling is very crude. Polyglossia presents its own problems, and it is still a very hard problem to solve, though much better than anything that you can get out of DTAC. The fundamental limit of this whole thing is that they parse, all four of them parse the source of a LaTeX document, but what we want is the text of a compiled document, and these are not the same thing. LaTeX is a programming language, and you can literally create a file that at every turn of a processing of it by LaTeX, it will produce a different output. It will change itself in order to produce a different output. So custom macros, input chains, cat code changes, floating code ligatures, language switches from packages, all of this makes sense after tech has run, but not in the source that you may have at your hands. So with a Pandoc stripper, we try to start with the LaTeX, go through a pre-filter that do the macro expansion, and marks the languages before you do any further processing, and then with a simplified tag, we take the markers and analyze them and separate them and deal with them in order to obtain separation of languages, etc. It's the only one that does separation of languages in a sort of a nicer way among the four in the set. The pre-filter, of Pandoc scans the preamble for a new command and does the macro expansion. I think it uses only 4 levels. Yes, only 4 levels. It detects language declarations and uses BCP47 tag map in order to mark them up, and injects certain tokens at language switches so that it can be later dealt with when you get a sort of a JSON file, or you get a tree that you can traverse and separate them, and strips the noise out, like things like label, to-dos, and include graphics and so forth, and then sends it out to be processed. And we have a math filter that also allows you to deal with the mathematics, or to just put a marker that area contains some mathematics in your new file, and also to deal with the issues of text within the mathematics, which also is extracted so that you can deal with it. The good of it is that citation handling is performed at a very high level. It's able to understand certain languages of certain of citations which are prepared appropriately, and then you can also send them and separate those later for text extraction. If knowing these limitations and knowing that we wouldn't be able to go much further with a lot of this, using those four preprocessors, I tried another idea, which was to create a stripper that would be parsed by LaTeX itself, by TeX itself, basically to be processed by LuaTeX, and allow LuaLaTeX to do with the text separation and the tagging and the ligature handling and so forth. And I kind of stole the idea from a package called Spellings, which is it's in the repository, and it's part of C10. Not very usable these days because of lack of maintenance, but that it does use this idea in order to do spelling of a source LaTeX file. And so the idea was, it looked good in the beginning. It would have zero overhead if it could be built. Custom macro expansion wouldn't be partial like the other cases; it would be full. Language separation will be exact, and font ligature could be dealt with, and footnotes could be dealt with. Noisy command stripping, and side command handling. Speed would be zero overhead, since one would probably be running LuaLaTeX already, and the only problem is the unit processing. So I settled on using a Pandoc stripper when no full build environment were available, quick extraction without compiling, and standard LaTeX and common packages were used, and then using LuaLaTeX stripper, which was a little bit more involved, using when I need exact language attributions, when I need custom font with ligatures, and I had a file which already compiled under LuaLaTeX. LuaLaTeX obviously, provides a whole environment, embeds Lua 5.3 interpreter inside, and any text build a node list for each paragraph. The tree that describes the text and the mathematics is readily available in there, so one can easily traverse it and obtain the information about text and mathematics. So we started out with a text source, go through a LuaTeX macro expansion, get a node list, and then with a Lua walker, we go into this node list to obtain the particular extraction, and then do the output on a per language field in text and in JSON. It has a Babel track, a Polyglossia track, so it has no information about BCP 47 languages inside. It uses the information which is inserted there by Babel and by Polyglossia, and which makes it, one of the first fully Polyglossia ready, fully BCP 47 ready programs in our multi-language environment. Lots of problems in dealing with it. There are LuaTeX has two renderers. One is the default render in Lua, the other one is HarfBuzz. They deal differently with ligatures, and so we have to expect both, and then proceed to analyze how to do ligature handling for each one of those. And then, you know, we had to deal with a few other things like language boundary space and footnote extraction, you know, and mathematics is once it's recognized, it's marked up in the text as mathematics or display mathematics, and BibLaTeX integration is fully ready. You know, you don't need to do anything besides marking up your text for languages, and you're ready to do this. You know, you can just use package stripper in a file, run LuaLaTeX, and then you get, you know, from mybook.tex, you can get my book en-us annotated.tex, my book extract.json, my book fr.tex, my book ja.tex for Japanese, and so forth, and have every single piece of text separated by language on the other side, with a parsing which is completely done by TAG. The two groups side by side, the stripper, the LuaLaTeX stripper is a clear winner, you know, by dealing with custom macros, math handling, you know, multilingual output, Babel support, Polyglossia support, you know, BCP47 native, and dealing with ligatures and footnotes and BibLaTeX citations with zero overhead is a clear winner. You can get access to it by going to my GitHub page, Paulo Ney, Pauloney, and downloading all 4 pseudo-handler strippers plus the stripper package under LuaLaTeX, and I hope you enjoy. Try it out and send us some lists of problems or wishes that you may have. Thanks very much for listening.
Yes, I do have the time.
Oh, good.
I just want to say I'm sorry for the malfunctioning of the slide during the recording. You can get, you know, the full set of slides at the website for the conference.
Hi, Paulo. Norbert Breining here. Thanks for your presentation. I'm always happy to see new text extraction features, because we are fighting a lot in archive, because we get a lot of, we have to text extract and do text overlap and this kind of stuff. Have you compared to PDF-6, which is one of the standard extraction algorithms? This is the one question. And the other is, how does it deal with these nasty little PDFs that contain like spirals and whatever other things? So that you can always work on LaTeX only. Does your code do anything on PDFs by itself, or only start from LaTeX?
Well, we may not have time for all the questions there. There's like 5 or 6 questions there. Yes, we did compare that with PDF-X, and the coverage on the 4 strippers, you know, the beautiful soup, you know, text soup, and then LaTeXML and so forth. The coverage does vary, and but it's superior to do anything on the PDF. It's superior, and but nothing compared to the stripper written for LuaLaTeX, because that is 100% accurate. You know, it's basically, you say, I want math, I want text, and you get math, you get text. And if you have your bibliography in, like, you know, 20 languages in your bibliography, you get all of that separated in 20 different files, marked up by BCP47, and everything's ready. I will try to address some of your other questions. what was the other question?
Now, for me, so we do normally text extraction from PDF, even if we start from a LaTeX document. That is not optimal because, well, we know there are a lot of problems there. How good does it compare to PDF extraction from PDF when you run it over the LaTeX source? Considering that it might have a lot of complicated macros and whatever, we get files that have every single word replaced with a macro, and so I'm not sure how good it deals with that.
Yeah, well, there's a divider here. You know, there are 4 strippers which are written for pseudo-parsers, and yes, indeed, you know, complicated macros botch things, and so LaTeXML is changing right now, and so we'll change accordingly, and hopefully, you know, we'll still cover most of the files. But yes, if you have complicated macros and if you have complicated stuff, it will botch those. The LuaLaTeX stripper is 100% sure. You know, there's absolutely, you can do spirals, you can make your text snakes on Tixie, and it will take those and serve them back to you as is.
Great, thanks.
Thank you.
Hi, Marcel Krüger here. I'm wondering, you mentioned that you have this handling for ligatures with the Lua renderer and the HarfBuzz renderer. And it seems like that is a bit unnecessary if you just hook in a bit earlier and just extract the text before the font shaping is happening. Did you consider doing that?
Well, I have to take whatever LuaTeX can offer me, and I have to tell you that you know, I'm not you know, I'm a mathematician and not a very well versed tech programmer, and so I may be missing something that would be easier to deal with. As you parse your, you know, the word differentiable over, you know, over LuaTeX, you get, you know, depending on the font that you have, you may get a ligature. Depending on the font that you have, you may not get a ligature. And so recovery from ligatures is a big part of the LuaTeX stripper right now. But I would be ready to listen to other ideas to deal with that don't have to read directly from the LaTeX source. I mean, reading from the LaTeX source is sort of a no-go because of the fact that LaTeX is not a markup language. LaTeX is a programming language. You know, we're interested in the text that shows up in the PDF. You know, I can write a LaTeX file that requires an infinite amount of processing in order to get the results that I need, the results that I expect. And so analyzing, you know, after the parsing by LuaTeX was the objective of the Lua stripper. But I'll write you, and I want to listen a little bit more careful to what your ideas are for not having to deal with ligatures, because that will simplify the parser tremendously.
Thank you.
Okay, perhaps we could thank the speaker again. Very nice talk.
Thank you very much.